As we do our volumes of revolution, perhaps the biggest task is making a sketch of the graph and getting a good perspective of what it is that we're revolving. In this problem, we're starting with one boundary, a line that has a y-intercept of 2 and a slope of negative 1/2. So perhaps like this graph. And our vertical lines are x equals 1, so go here, and x equals 2. So, and the x-axis is another boundary, so we're taking this region here, I'll highlight it, and we are revolving, we're spinning this around the, trying to get a different color stylus here, we're trying to revolve this around the x-axis. So each of these will come up with a mirror image on the other side, so might help here if we see kind of circular ends here. So if we revolve, and I kind of have my perspective here a little backwards, so let's maybe make this bold, see if that looks like we've got some perspective here of revolving this thing. And then in each one of these cases, what you have to do is show us a typical Riemann rectangle. So remember, choose a spot somewhere in the middle of your graph, my line back there, and make a rectangle. And again, that will remind you that our thickness here is a delta x. So we'll have x as our independent variable, which makes sense. If we choose x, some generic x coordinate, then our y coordinate here comes from the equation of that line. And that is going to become the radius. As we revolve, we will come up with disks for each of these cross sections. So if we let those circular disks go across from 1 to 2, to accumulate all of those disks, we need an integral from 1 to 2 to get our volume, accumulate all of those circular disks. So remember, what each disk looks like is a cylinder with that delta x as its height and its radius from the x-axis up to this function. So the radius of each of those disks is our value 2 minus 1/2 of x. So we're doing pi r squared here. We're just adding up a bunch of circles, and they become cylinders, three-dimensional cylinders, because this is the thickness of each cylinder, or the height of each cylinder. So those discs or coins are each a cylinder. And then we can, if we was a calculator problem, just go ahead and use your calculator to plug this in, but we'll do a little arithmetic here, a little algebra, sorry. So let's square that binomial. The product here would be negative 1x, so we'll double it. And negative 1/2 x squared will be a 1/4 x squared dx. And then we can do our antiderivative. Let me give myself a little more room here. So that would be a 4x, raise that exponent to 2 and divide by it, raise that exponent to 3 and then divide by it or multiply by 1/3. And then we evaluate from 1 to 2. So we've got a little bit of arithmetic to do here. Put 2 in and we'll have an 8 minus a 4 plus an 8/12, and you could change that to 2/3, but we'll wait and see. I think there's going to be a 1/12 in the next group, so I might as well keep my common denominator. And then put 1 in, and we'll have a 4 minus 1 plus 1/12. So that was what I was thinking about, keeping the 1/12 here. And a little bit of arithmetic here. Do you notice this negative 4? This, when we distribute, will be a negative 4, so it'll cancel with that 8. So let's make sure we get that this is going to be a positive 1. And then we've got positive 8/12 minus 1/12. So we've got a positive 1 left and a 7/12. So how about if we make this 19/12 pi? And we don't know the units, so we don't need to label it, but it's a volume. So when you do know the units, make sure that you would put cubic units there. All right, let's try another. Find the volume of a solid if the region formed by this upside down parabola and the line y equals 0, that's the x-axis. So if it's revolved around y equals 0. So it's the parabola that has its y-intercept at 1. So it's this parabola. And we're taking the region of that parabola bounded between the x-axis and the parabola. And we are spinning it again around the x-axis. So we'll get a mirror image down here. And then if we draw a typical rectangle, wherever you would like to draw it, and then we show the idea of what happens when we spin this. And you can draw more than one of those if you wish, but remember that this will be a solid, so each of these. So if you're an art student, go ahead and do some shading there. But we'll come up with these discs, and this time our radius is still, again, our radius comes from the function, so our y coordinates are the 1 minus x squared. So that is the radius of each of these. So what we need to do then is say, well, how far are we accumulating these? And here we have an even function, so instead of going from negative to positive, you could go from 0 to this limit and then double your volume. This intersection, where is this x-intercept, I should say? Well, when is 1 minus x squared equal to 0? And I don't think you would have to show your algebra. I bet you would have guessed that that was at 1, 0 and at negative 1, 0. So to find our volume, we are accumulating circular disks, and I'm going to go from 0 to 1 and then double the volume because it is an even function. It has symmetry to the y-axis. So my pi r squared, our radius, is the y-coordinate here. So we've got to square that binomial. So again, you can bring the pi out in front and put it back in your answer later if you wish. And again, we've got a binomial to square. So let's distribute here to get our trinomial. And then integrate. So this will be a 1x, and raise this exponent to a 3 and multiply by 1/3. Raise this exponent to a 5 and divide by it or multiply by 1/5. And here, starting at 0, you can see the advantage. Oops, and my pi turned into an x, sorry. That should be a pi. So the advantage of doubling is that when we put 0 in for all of these x's, we won't have to worry about our second parenthesis. So when we put a 1 in there, we'll have 1 minus 2/3 plus 1/5. And then just to make it clear, our second value would all be zeros is what I was saying there. So we could either convert here decimals. We'd have to do a repeating decimal, so I think I might make the effort of just sticking with fractions. So we might do 15/15 minus 10/15 plus 3/15. So we will come up with 8/15, and then we have to double it. So 16/15 pi. You can always check my arithmetic. And number 3, we need to revolve again around the x-axis. So we better soon practice some revolutions around the y-axis. It won't always be this. We have a parabola, 1/4 x squared. So it's a parabola that is wider than usual. And of course it would go on the negative side as well. Our boundaries are at x equals 2 and y equals 0, so our x-axis. So we've got the x-axis is the line y equals 0, the vertical line x equals 2, and our function. So there's our region, and we're going to revolve it around the x-axis. So we will come up with a mirror image on the other side. You might find it easier to do that first, or you could do that second. So this is going to be an open, like the bell end of a trumpet here, if we revolve this region. So it's going to look like a circular end on the end of the solid. All right, and then our typical rectangle, let's go backwards a bit here, and let's revolve it. So if this is our typical disk, we know we're going to be going from 0 to 2. And we simply have to accumulate all of those disks, and our radius is, when we revolve around the x-axis, our radius is quite simple. Our radius simply comes from the y-coordinate here, because it goes from that point down to x comma 0. So our volume is accumulating all of these disks from 0 to 2. Pi r squared, our radius, is our y-coordinate. And again, I'll bring the pi on the outside. So we will have 1/16. Could I bring that to the outside right away? Might be worth it, might not. X to the 4th would be the only thing left inside if I bring the 1/16 out of the radical, or out of the integral, sorry. And now we do our integration, our antiderivative, raise the exponent to 5, multiply by 1/5. So we could bring that 1/5 out here also. So we would have pi over 80, and then we would have 2, we'd only have x to the 5th left to go here, so from 0 to 2. So we would have pi over 80 times 32 minus 0. So we can cancel there by 16. So we would be back to 2/5 of pi. So you might do your arithmetic differently, but eventually you'll come to something that's equivalent to 2/5 pi. And it is a volume if you want to add cubic units. Eventually we'll get to some applications, and then we will know the units. All right, now it says be careful. This region is revolved around the y-axis. So here we go, and our diagram's already made for us. So we're taking the region bounded by x cubed. Remember what x cubed looked like. It's positive in quadrant 1 and negative in quadrant 3. X cubed is an odd function. And it's also bounded by x equals 0. That's the y-axis. And the horizontal line, y equals 8. So here we've got, in this picture, this blue color is what I've been shading. So that's the region that we are revolving. So we're spinning it this time. We're taking that region and spinning it around the y-axis. So if I was going to draw that, my very poor diagram, it would, I'd start with this diagram. I would highlight or shade this area, and I would pick a typical rectangle. Notice that the thickness now of our rectangle is a delta y, the distance across that rectangle. And when we revolve this, when we spin this around the axis, so it's going to become a solid here. I'll make this darker, it's towards the front. And when we spin this rectangle, we will get a typical disc right here in the middle. So there's my diagram, so you'll know it doesn't have to be as perfect as the one you just saw. All right, so if we actually stick with that, we know that this line up here was y equals 8. So our coins or discs are elevating from 0 up to 8. So now we're adding up all of those pi r squared dy's. So this time our volume is going to go from 0 at the bottom to 8 at the top, and our thickness of our cylinder is our dy. The delta y becomes our dy in our integral. So this time we need pi r squared. Well, look at what the radius is. Here's the radius of our disk. So this time the radius has to be the x coordinate. So we want to take our function. It was given as a function y equals x cubed, but we want to reverse it. So we would take the cube root of both sides. So we have to solve the equation so that y is our independent variable. So now the x coordinate would be the cube root of y. So that is our radius. The cube root of y is the radius of this value. So hopefully you see that I'm measuring this distance. This is our radius. So pi r squared for each of our disks. So cube root of y, pi r squared. And that's all there will be to it, and we can change that to a power rule. So this is y to the 2/3. So let me write that step. So change the cube root to a 1/3 power, and then we'd have power of a power. So we'll have y to the 2/3. So integrating, I'm going to raise that exponent by 1, so it'll be 5/3, and then divide by that, so we'll have a 3/5, which I can bring out in front. 3/5 pi. And then we want 8 to the 5/3 power. Well, notice what that is. That's the cube root of 8, which is a 2, and then we can raise it to the 5th power. And then, of course, 0 to the 5/3 would just be 0. So the cube root of 8 becomes 2, and 2 to the 5th power becomes 32. So it looks like we could write this as 96/5 pi. And again, optionally, we don't know the units, cubic units. And that should be our examples for now.